Okay, everybody. So if we look at, hold on here, let me get the Zoom stuff out of the way so I can actually do this. All right. Um, so if you look at the course assignments, we have these zyBooks assignments available, Chapter 2, Chapter 3. Chapter 3 is due next week. So there's a lot of stuff that I want to go over from this chapter, and we'll just kind of jump into it. So we'll go to Chapter 2 first, just to look at the last section that we have. In Chapter 2, we have 2.1 through 2.9 here, but actually the exercises only go to 2.6. And where I'm going to jump into is 2.5. So we'll just do 2.5 basically, and then jump into chapter 3. So 2.5. Let me just double check that we're recording. We are. Okay. So in 2.5, they're talking about computer performance a little bit. They're talking about optimizing performance. And there's a rule in here that I think is useful. And so I figured we would just mention it before we moved on to chapter 3. So what the rule has to do with is how much of an improvement you're going to get if you are optimizing some computer code. So in this example right here, they've got kind of a graph, or not a graph, but like a picture representing like the execution time of some process. Okay. And so what they've got here colored in orange is going to be how long it takes to run an add operation. And in the blue, it's all of the other operations. Okay. So it says it right here. So basically 60% of the time we're running add operations and 40% of the time we're doing something else. Okay. Um, and then what they're trying to get across here is that if you were to improve the add instruction by 2 times, right? You're like, okay, it's twice as fast now. Um, but your entire program is not twice as fast, right? Because if you were to improve the add operation by 2 times, it makes the orange bar smaller because the orange bar is the add operation, but the blue bar stays the same length. So you still have this like 40% of the time, whatever it was, it's still going to be 40% of the time. Um, Not 40% of the new total time, but 40% of the original time. And so basically the orange bar gets shorter because you made the orange faster, but the blue bar does not get shorter. Okay. And so even if you made the orange bar disappear, right? We make it twice as fast, we make it twice as fast again. And even maybe we took it out and made it take no time at all. You still have your final execution time is still 40% of what the original execution time was, right? Because we didn't make the blue bar any faster at all. And so that actually has a name. And so here's the name, Amdahl's law. And it's basically just the math that has to do this. And as far as that goes, I wouldn't necessarily say that we need to memorize any kind of formulas here, really. Um, you just need to understand what's actually happening here. And so the rule as written here says um, the performance enhancement possible with a given improvement is limited by the amount that the improved feature is used, right? So you need to optimize only the stuff that you're running the most. Otherwise, you're not really going to get a benefit from it. That's the key thing. And that's why if you were doing programming, right, like what you would do is to optimize a program, what you would do is first of all, measure, or actually the correct word would be to profile your program to see where uh, it is spending time, right? So which functions are running the most, right? Which methods, functions are running the most. Again, Zoom stuff's in the way. 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 Oh, why? Where's the stupid word wrap? I know it's here and I'm blind. Well, I can't see it. So, all right. So, you got to know which functions are running the most, right, in time. After you do that, then what you would do is you want to optimize the ones that are right, speed up the functions that you are spending the most time doing, right? And I hope that makes sense, right? So you don't necessarily need to optimize your slowest function, right? Um, so you don't need to optimize your slowest functions necessarily, um, right? Because if they run rarely, they may not matter. So that's just something to keep in mind. Um, but then you can do a little bit of math for things. And so if we wanted to do something like this, a program runs in 100 seconds. Multiply operations are responsible for 30 of the seconds. If the extensive designer effort is applied such that multiply operations are made to run 2 times faster, what is the program's new execution time? Um, so when you see something like this, uh, that's not that. It says no live Zoom today. Um, so how would you do something like this? Well, it says the program runs 100 seconds. Okay. Multiply operations are responsible for 30 of those seconds, right? So at the start, what you have is you have 30 seconds for multiplication, right? And you have that means that you would have 70 seconds for other stuff, right? And then after they said that if extensive designer effort is applied such that the multiply operations are made to run 2 times faster, what is the program's new execution time? Well, if we make multiply 2 times faster, then instead of running in 30 seconds, it's going to be 15 seconds, right? That'd be twice as fast. But the other stays the same. So you'd still have 70 seconds for the other. Um, so your total, right, would be 85 seconds at the end. And I didn't use any math formula here to do this, right? I just said, okay, well, they told us 30 seconds for multiplication, 70 seconds other stuff, right, to add up to the 100. And then they said multiplies twice as fast. So instead of 30, it's going to be 15 because that's twice as fast. The other one was left alone. And now altogether, you have that 15 seconds plus the 70 seconds or 85 seconds. And so if you come over here and try to put this in to check the answer, you'll see that we get it right. But the way that they did, like the way they try to explain it with a math formula is, I feel like a little bit confusing, right? Like, yes, you could use this. Like the execution time is the execution time affected, which is the 30 seconds for the multiply. The amount of improvement, well, it's 2 times as fast, right? So the 30 over 2 is that 15 seconds. And then they say, plus the execution time of the unaffected stuff, that's the other. The other was 70, right? Which we mentally had to do 100 minus 30 to get that. But when you write it all out as a formula, I feel like it seems a lot more confusing than it is. Um, so here's another question. I mean, we can just click the button, of course. But if some stuff's always in the way. If some aspect of a computer accounts for 50% of a programming time or a program's execution time, what is the limit on how many times faster the programs can run if the engineers focus on improving that aspect? So basically, I'll say the aspect or that aspect, right? That's going to be, let's say, 50%, right? 50%, that aspect. That means 50% is other, right? To add up to 100. So um, if we used magic, so this would be like the before. Now, let's say we afterwards, somehow we make that aspect, whatever they're talking about, run instantly. So now it takes 0% of the time, right? We just made it instant. Well, we still have the 50 of percent of the other stuff, right? So in terms of the total, so before the total was 100% of the time, right? 100% time. And after the total is 50% of the time, right? Because we made that aspect run instantly, but it was only half the time. So we actually went from taking however long we were taking, 100% of the time, and now we're taking 50% of that time. So that's actually twice as fast, right? So 100 over 50 equals 2. So that's going to be twice as fast, right? So even if you're optimizing something that's taking half the time that the computer is doing, the best you can do is make your program twice as fast, right? Um, and that's really just all there is to it. So that's just something to be aware of in terms of optimization. The rest of the stuff we can just kind of read through. Power efficiency matters at low utilizations because servers workloads vary. Okay. Computers at low utilization use little power. I mean, that's more true now than it used to be. Their citations are often low, but as they're saying in here, um, computer in 2020 uses 33% of its peak power at 10% load. So yeah, it's still significant power, like 33% of its max power, even when you're not using it. Okay. Um, let's see. Let's see. Blah, blah, blah. Google's warehouse's scale computer uses 5% of peak power when running at 10% utilization. I guess that's what we just read. That seems false. Um, Designers must choose between energy and performance. The computer is designed for improved performance. The computer's energy consumption will increase. Those are unrelated. Um, okay. MIPS. This is an old measurement for performance of a computer. MIPS, millions of instructions per second. And so they have a formula here. You've seen some formulas like this in other sections. So it's the clock rate, which would be the speed that the CPU is running. And then you can divide by um, the CPI, right? So, okay. Here they're okay. There's nothing really to do here. They're just trying to calculate this. So, like when they say which computer has a higher MIPS rating, so you have to calculate it using the formula. So it's going to be the clock rate um, divided by the instructions. Hold on. um, Times 10 to the sixth. So let's see, we get a calculator. So you'd have to do these to compare the MIPS rating, how many instructions per second they run. So on the first case, computer A here, we want to run 10 billion instructions. That's the instructions on the bottom. The clock rate is 4 gigahertz. Um, so 4 gigahertz is 4 billion. They're both 4 billion. So 4, 1, 2, 3, 1, 2, 3, 1, 2, 3. So there's your 4 billion. I could have used the maybe times 10 to the whatever. So we have the clock rate. Then we have to divide by the number of instructions. So here the instructions is 10 billion. So we have to divide by 10 billion. 10, 1, 2, 3, 1, 2, 3, 1, 2, 3. Um, let's see here. We get 0.4, but then we would have to 0.4 times 10 to the sixth. So that would be, let's see, we have to wait a second here. Oh, oopsie. Did the calculation wrong. The instruction count we have to multiply by the CPI here. Um, 1 second. I'm going to pause this. Are we recording again? I can't tell. Okay, I think we are. Um, all right. So, yeah, they didn't give us clocks per instruction. So, oh, they did give us clocks per instruction. Oh, oh, okay. Sorry. I don't know what I was talking about for the last couple minutes. Um, yeah, I was trying to use this the formula here, and so I was putting in the clock rate, and then for the CPI, I put in like 10 billion for some reason. But we don't need that, right? Like we actually just need the clock rate, which is 4 gigahertz. That's how many clock cycles you have per second. And then the CPI is clocks per instruction. So if you have the 4 gigahertz and the 1.0, that's enough already to calculate the MIPS, because MIPS is just millions of instructions per second. So how many instructions we're running, 10 billion or 8 billion, um, that doesn't matter in terms of the MIPS rating. Um, they can just be whichever one's faster is going to be whichever one can do it in. Well, we can answer that question when we get to it. But yeah, so let's start over here. To actually calculate the MIPS rating, what you would do is just what it says here. So you need the clock rate over the CPI. So for computer A, the clock rate is 4 gigahertz. So that is 4 billion, right? So 4, 1, 2, 3, 1, 2, 3, 1, 2, 3, 4 billion. You have to divide by the CPI, which is 1.0. So obviously dividing by 1.0 is going to do nothing. But because it's millions of instructions per second, you also have to divide by a million. That million, right? The 10 to the sixth is a million in the denominator. So um, divide by another million. So 1, 1, 2, 3, 1, 2, 3. So that would be dividing by a million. And so this is 4,000. Okay. So computer A is 4,000 MIPS. That's what we have there. So A, 4,000 MIPS. B, what's B? Well, we would do the same calculation. We're going to be dividing the 4 billion by 1.1. So where's my calculator? Here it is. So you'd have to do 4 billion, 1, 2, 3, 1, 2, 3, 1, 2, 3. divide that by 1.1 this time, you get this. And then you need to divide by a million again for the million in the denominator. So 1, 1, 2, 3, 1, 2, 3. There you go. And you get 36 MIPS. So you get 36 MIPS. So 3,000 instructions per second. Okay. So which computer has the higher MIPS rating? Computer A, right? 4,000 versus 36. Now, which computer is faster for the program, though? So this is 10 billion instructions, and this is 8 billion instructions. So if you think about it, um, so if computer A takes, what is it, 10 billion? 10, we'll say B instructions. Well, if it runs 4,000 MIPS, then we can just take the 10 billion instructions, um, divide it by the 4,000 MIPS, and we could find the execution time, right? Because this is instructions per second, and this is instructions. So you would take your 10 billion instructions, so 10, I'll say billion, and then you would have to multiply it by, um, well, I guess divide it by technically. You would divide it by uh, 4,000, and that is MIPS, which has millions of instructions in the bottom and seconds. Sorry, yeah, millions of instructions per second. So we're going to put that in the denominator. The result is going to be some number of things, and it's going to be in seconds in the numerator when you multiply that. So like the billion, this is instructions in the denominator. Um, but then it's instructions over seconds, which seconds will end up in the numerator, if that makes sense. So the main point there is you have to, if you actually wanted to work out the math there, is you'd have to take the 10 billion, so 1, 2, 3, 1, 2, 3. Probably should have used a calculator where I just type in scientific notation. Um, it's right there, actually. So there's your, that's 10 million. There's your 10 billion. And then you would divide by 4,000 MIPS. So that's actually 4,000, but also MIPS means million. So you'd have to divide by 4,000. So you get this, but then you'd also have to divide by a million. 1, 2, 3, 1, 2, 3. And you would get that, which is 2.5 seconds, basically. 2.5 seconds. Now, computer B, I'm not going to flip back there, but I remember that it said it took 8 billion instructions. So that would be your 8 billion divided by the 36 MIPS. And also we'll get seconds, but we have to do 8 billion, 8, 1, 2, 3, 1, 2, 3, 1, 2, 3, 8 billion divided by 36. So we get that. And then we have to do divided by a million again. And we get 2.2. So this is 2.2 seconds. So it's 2.5 seconds versus 2.2 seconds. So the first computer is 4,000 MIPS, but the second computer actually runs this program a little bit faster. Um, and so this is you see 2.5 seconds versus 2.2 seconds. So I guess what they're trying to show you here is that two computers could have the same number of MIPS quoted, but still technically like that second computer actually runs this program a little bit faster. And that's more or less because two computers have different lists of instructions that they can run to like different processors. And so even though computer A runs 4,000 MIPS, that's millions of instructions per second, and computer B only runs like 36. The instructions in computer B, they must be more complicated instructions that do more work. So uh, measuring number of instructions per second is a useful indicator of performance, but it's not necessarily that the computer with the most MIPS wins. And this was just an example of that. So computer A runs more instructions per second, but computer B was faster in practice. Okay. So that was just the very end of that section. I just wanted to talk about Amdahl's law mostly. You can read the concluding remarks here. There's not much to it. I want to do a little bit of chapter 3 now. Now, I think what I'm going to do is we'll do 3.1 for sure, but then I don't know if we can do 3.2. I don't know if we can do 3.2 because of the time. So we'll probably be doing that in class instead of just in this video. All right, but we can look at this. Let's look at 3.1. So bits, zeros, and ones, you should be familiar with this. A single 0 or 1 is a bit. I hope you know this. If you group them, 1 0 1 1, that's 4 bits, right? 4 zeros or ones. 8 bits, which they have there, that's a byte. This is just terminology, very straightforward. Um, so bits 0 1 is called a bit. 8 bits is a byte. And this has 1, 2, 3, 4, 5, 6. If I can count, 6. And we can. Okay. Now, ASCII. So you probably have seen this if you took CPSC-06 or 14 here. I think it's in the Xi book for that as well. But an old standard for text was ASCII. So back when computers were new, um, they were trying to figure out how many bits to use for characters on a keyboard. And if you think about it, here's how you could think about it, right? How many bits for keyboard characters, right? How many do we need? Well, think about it this way. Um, so first of all, you have your letters, right? So lowercase, that's 26 letters, right? So we're just adding up how many things we need. We need lowercase letters, 26 of them. Uppercase letters, 26 of them. Okay, digits, that's 0 through 9. So there's 10 of those. Um, Now punctuation. So punctuation, that'd be like what? Like parentheses. So there's two parentheses, square brackets. So that's two of those. So we're at four. Um, Question mark, that's five. Period, that's six. Exclamation, that's seven. Um, I don't know. Are there more? Yeah, there are. There's like semicolon and comma. So I don't know. Let's just say around 10 punctuation things. And then you could have like other symbols that might be useful. So like asterisk, ampersand, pound sign, at symbol, other stuff, triangular brackets, slashes, right? So there's quite a few of these. I mean, I don't know. I'm just gonna say like 15, just a guess there. Now, when you add these all up, what do you get? You get like 26 and 26 is 52, plus 10, 62, 72, 80 something. I don't know. Did we get 87? I don't know what I ended up to. I think 87, right? 87 or so. Now that's just ballparking it there, but that's about how many things we need. Maybe plus some extra, right? Now think about that though. How many bits does that take? Well, you would calculate it with 2 to the whatever, right? Is how many things you can represent within bits. Okay. So what that means is, if you have one bit, you can only represent two things, right? That makes sense, a zero or a one. But if you had like two bits, now you can represent four things, right? I'm not going to keep writing it out, but with four bits, right? 0, 0, 0, 1, 1, 0, 1, 1. Those are the four things you can represent, right? Now you keep doing this. I'll skip a couple. I'll go to 5 bits. 5 bits would be 2 to the 5, which would be 32 things. Okay. We need to get to at least 87 though, right? So 6 bits, that'd be 64 um, things we can represent. 7 bits, that would be 128 things, right? 8 bits, that'd be 256 things. Okay, so if you have about 87 or so, maybe plus a little bit, then how many bits would it take? I mean, it would take basically 7 bits, right? So keyboard uh, needs around 7 bits to represent all the characters we care about. You know, and then that's where you put like the little asterisk on there. And then in the footnote, you say, as long as everyone types in English, right? Because of course that's a big weakness of, what we just did here, right? We said 26 letters, um, which is not always the case, right? Especially you have accent symbols in European languages, you have other alphabets. Then if you go into things like Arabic or some Asian languages or things like that, then they need way more characters than 7 bits. But at the beginning in 70 something, they did not care. Uh, so they used 7 bits. So you'll see that they used 7 bits because that made sense. 128 characters, that's plenty. And so there's this chart that you can look up here, but you can also look it up everywhere, like, just by Googling ASCII chart, basically. And you'll find it all over the place. But here's one right here, and it's going to be just what 7 bits match up with what character. Now, on a modern computer, we generally store those as a byte because 7 bits is awkward to work with. Everything wants to be in powers of two. So even though this is 7 bits, I think people will generally represent it with 8 as a byte. Um, All right. Now we're not doing too much here. So like what is a 7-bit code for lowercase a? So they just want you to come up here and look it up. So like you come up here to the table where which binary number matches up with which symbol. You would just look in the right column for the lowercase a. And so you find like the lowercase a over here, and it's 1100001. So you'd say 1100001. Yeah. And they want you to notice that lowercase a and uppercase a are different. That's because these are just keyboard symbols, right? Um, they're different letters, right? They're different symbols. So you can look these up. What is the 7-bit code for blank space? So it's not blank, right? First of all. So when you type a space, that's still a key on the keyboard. We have to represent it. Where is it, right? So you find it here somewhere. So we just scroll until we find the one that's blank. Oh, it's actually at the beginning, space 0100000. Oops. 2-letter word does this represent? So this you'd have to look up. So 1001, 000. So you just have to look it up. So 1001. So we look here, like look at the beginning of the letters till we start to get to 1001. All right. Here's 1001. Actually, 1001000. I think this is it, right? So that's the first number we were looking for. It's capital H. Next one, I mean, it's probably I, right? But lowercase or uppercase. So this one's 1101001. 110. So we're looking for 110. All right, so 110s are over here. And then what are the last three characters or four characters? 1001. 11001. Lowercase I. Okay. Uh, suppose an email message has 500 characters. How many bits would a computer use to store that email using ASCII code having 7 bits? They want you to do 7 times 500. I get like 3,500. Right? Okay. So here we're just looking these up. So like Z, you just look up Z up here. Uh, look, just copy paste it. Don't type it. What's a three? Notice that three is not like binary number three or anything like that. So you're looking for three, so you find the three. There it is. I pasted. Put it there. What's this? Now we got to look it up though. 110 0010. 110 0010. I think that's this. B. I went over to the right side, by the way, just because like the way I was able to do that um, was by sort of remembering that like the way these columns were set up is this first column started 010, and this started 100, and this started 110. So when it said 110, I was like, oh, it's going to be over here with the lowercase letters. And I was able to go to mostly the right spot. Same thing here, right? This is 010. I think that was all the way on the left. And then 1110. 1110. I think that's here. So is that a period? If I get it wrong, then I get it wrong, but yeah, we got it. Okay. Um, I'll just show you this just because I happen to remember it right now. Um, I saw this like I saw a clip. Um, beetle aired. If I can find it. No, 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 no. I don't know if I'm gonna find it. Ah, this is a clip from somebody. It's a 10-minute clip. Um, but I'll find it. I'm gonna click on this and we'll click to it. It'll take me a minute. I'm gonna turn the volume down while I click to the right place. Um, so if you don't know who this guy is, there's this guy called Vettel. His Twitch stream is Vettel987. I don't watch him, but I occasionally see clips like this. And so basically, this is an AI. He has two AIs that stream for him. And the only reason that this is important is because um, he told it to write a blog. And oh, yeah, so it'll probably be right here.
You know what? I
don't know if you can hear
scares the
this.
life out of me.
I'm just
What
realizing.
the hell does that say?
Oh yeah, so he told it to write a blog, and it wrote a blog, and it wrote the blog, and it says, "Follow the adventures of everyone's favorite AI." Latest blog post. I hate, and then it put ASCII there, and so he just looked at the website, and He's like, what? Wait, what is that? What word is that? He's like terrified that it just said something horrible because, that could happen when you're using AI to do stuff. So, yeah, but it's actually, I think, frogs, because like her blog post said, hold on, I should probably elaborate. Frogs are one of the worst species of amphibians ever to walk or rather hop this earth. So it said frogs. I hate frogs. Why? Who knows? Uh, but it was pretty funny. I saw that the other day. So anyway, see, ASCII in action. That's the point. So it still matters. So he had to go look that up on like an ASCII to text converter, which you can find as well. So you can say like text to ASCII. Um, so you can find these like frogs. Um, wait, text to that is this, I guess. Close. What? This is not working the way I wanted it. Okay, well, forget it. I don't like the way that this calculator was doing this, but there are converters that will convert to and from ASCII, so you can look at the binary version of the code. All right. How many characters on the text displayed on the screen on the left side of the animation? Uh, well, if it's going to display this, 1, 2, 3, 4, 5, 6, 7, 8. I'm going to say 8 without watching the animation because there were 8 in the picture. Notice that things like space are still a character. Even though they're empty, right? It's still, you had to have the space there, otherwise it wouldn't put an empty space. So a space is still a character. How many memory locations are used to store the text? Um, that should also be the same number, 8. The first letter is S. What bits are stored in the first memory location? Um, right, they're just the ASCII code that's there. What is the minimum number of bits that each memory location must be to store the example above? Well, this was ASCII, right? So if you count them, you'll see that they were 7 bits. Um, so 7. How many total bits were needed to store? We need, well, there were seven bits per memory location. And as we said up here, we counted the letters and there were 8. So 8 times 7. So you would need at least 56 bits, right? Okay. Now, the thing about ASCII, and I sort of implied it when we were looking at this, when we said, keyboard counts around, uh, we need around 7 bits to represent all of our characters. Um, and then I said, as long as everyone types in English. But of course, eventually, after a few decades, people realized that not everybody in the world does speak English. And so they finally got around to doing something about that. And so they came up with the Unicode standard. Now, the Unicode standard is what we use now, and we've been using it for quite some time at this point. However, the way that Unicode works is very complicated. Um, so with Unicode, first of all, there's more than one numbers of bits. So there's like 8-bit Unicode format. There's like 16-bit Unicode formats, etc. If you had a 16-bit Unicode format, you could store 65,000 characters. But there's no definition for this is the 65,000 characters we're going to store. They don't have that. So there are a lot of different versions of Unicode. So, like if we go Unicode standards and you try to find them, you can't just get like a list of tables. So like where's um I don't I don't know. I don't want to get into the weeds here, but well, actually, this is kind of useful. So, like in the first version, they supported these scripts. So, like all the characters they would need. So, like for Japanese, they had hiragana. Um, you see, no, no. we guess we do have Chinese and we have Korean in there too, right? But as they went on and we got newer and newer versions, eventually we ended up with most, modern like languages that are still spoken or at least written, have um, symbols available. Now, that doesn't mean you have a font to display all those, but you have you have the ability to represent them with the Unicode standard. But it's not really one standard, like I said, like you can have different number of bits and all that stuff. So they use different language to refer to things because of that. So, like it says, characters in Unicode are represented by a number or a code point. And here, this looks like a um, brain not working. I think a 32-bit format here. I'm saying 32-bit format because I assume this is like hexadecimal, and so 16 times 16, so 16 per character. So I think that's like 16, um, 16 times 16. I don't know what I'm saying now. Um, Yeah, okay. So we get down here, then they're talking about what I was just mentioning. So there's UTF-8, UTF-16, UTF-32. Those are what they call encoding standards. So that's how to represent the symbols that you are going to display. So UTF-8, um, characters are stored from 1 to 4 bytes. UTF-32, all characters are stored as 32-bit values. Now, the thing about UTF-8 is that they're stored by 1 to 4 bytes, but I believe that the reason they did this, 1 to 4 bytes, was so that if you're using 1 byte, then the character codes, I think, would be the same as ASCII. Don't quote me on that, but I think that was the point. So there's a lot of different ways to store this, and so the documents need to be specifying which version they're using. And they're showing you as an example of that, like a web page might have a little thing like this. It says meta character set UTF-8, just to indicate how the rest of the text is stored. So we're not doing anything fancy here with Unicode. Just be aware that Unicode can store like all these different languages of characters. That's the main thing. And that is confusing and hard to work with. So here it says like, how do you do a P? So you find P 0050, and so it's there. What's P in ASCII here, which was 80, so it was not a 50. uh, U plus U is for the Unicode 0020. So we look for 0020. So we find 0020 here, it's space. Um, what is this? Well, you have to look them up. So 0061. 0061 is somewhere. Here it's lowercase a. So it must be this because it couldn't be the other one. Each character is stored as a 16-bit value. No, there are different encodings. So, I mean, you should be able to do this yourself, right? Like, what's a B? So you just come up here and you look for lowercase b. It's 0062. So you put that in, and so on. You know, what is 002D? Remember, there's going to be letters in there because it's used as hexadecimal, even though we haven't talked about hexadecimal yet. But what was it? 002D? It was a dash, I guess. And there you go. Okay, so the next section in here is 3.2, which is number bases. And I'm going to actually lecture on that today, which is Tuesday, September 23rd, 2025. So I'm gonna lecture on this in class today. Okay. So that way, I think that will be helpful for everybody. So we're going to be talking about how to convert from any base into a decimal. And we're also going to be talking about how to convert from a decimal to any base. There is like kind of a shortcut to it, which is why I want to make sure I go through the steps. And I think that'll be helpful. And then the next section after that is 3.3, which is binary, hexadecimal, and octal, which are just three particular bases. So if you can do one of them, then, or if you can do the previous section, then you can do this section as well. So I think that'll be helpful. But I'm going to have to stop this video here. So I will talk to you guys later.